Welcome to the video module of microprocessor and microcontroller subject. We are going to learn about 8086 microprocessor architecture. So 8086 microprocessor can perform 16-bit data operations. To access any data from the memory, it requires 20-bit address. 8086 has the capacity of parallel processing. So the 8086 microprocessor architecture can be divided into two parts: bus interface unit and execution unit. It is a 40-pin IC. To perform any function within this microprocessor, it will undergo 4 CPU cycles: fetch, decode, execute and store. So the instructions which will be available on the memory will be taken during the fetch cycle, and it is decoded as machine understandable language and kept ready for execution, and the execution will be performed in ALU unit, which is available in execution unit. After performing the arithmetic and logical operations, so the result should be stored in the memory. So for any instruction to be performed or any function to be performed here undergoes these 4 CPU cycles. The fetch and execute will take place during the same time. As the particular instruction is executed in the execution unit, the next instruction to be executed will be fetched from the memory. So this is considered as parallel processing, which leads to speed up the microprocessor operation. So the bus interface unit is used to communicate with the external devices such as memory and IO devices. The bus interface unit provides the path to send or receive the particular data or address based on the read and write control signals. The execution unit is used to do the arithmetic and logical operations. Whatever instruction to be executed in the execution unit will be fetched by the bus interface unit, and it is decoded and kept ready for execution. So this picture shows the internal architecture diagram of 8086. The part above this dotted line indicates bus interface unit, and the part below this dotted line indicates execution unit. The bus interface unit, it has segment registers, instruction pointer, physical address calculation part, a instruction queue, and memory interface for connecting with the external memory. In the execution unit, it is having general purpose register, index register, arithmetic logic unit, flag register, control system and instruction decoder. So for this 8086 microprocessor, since it is having 16-bit data, it can access 16-bit data. The whatever data to be taken or placed on the memory will be accessed with the 20-bit address. So 20-bit address lines are available with this 8086 microprocessor. So based on 2 power 20 calculation, 1048, so 1 megabyte of memory can be interfaced with this 8086 microprocessor. The 1 megabyte of memory can be divided as 4 segments. The total 1 megabyte of memory can be divided as 4 segments. So the 4 segments are code segment, data segment, extra segment and stack segment. So the code segment is used to store the program, and the bus interface unit is used to fetch the instruction to be executed from this code segment, and whatever subprogram available in the main program will be stored in the stack segment. Also, the intermediate result for accessing the subloop program will be stored in the stack segment. So the data required for this program will be stored in the data segment, and the extra segment is used for string data operations and for subloop operations. The entire 1 megabyte of memory is divided as these 4 segments. Each segment is having the capacity of 64 kilobytes. So each segment has 2 addresses. One is segment address, another is offset address. So segment address is the address for the entire segment, and offset address is the individual memory location address. So the entire segment address will be stored on the segment registers. So the individual offset address will be stored on the instruction pointer whenever it is executed. So in the architecture we can find 4 segment registers: extra segment register, code segment register, stack segment register, data segment register. So whatever address available for that particular segments will be stored in these 4 registers. The segment registers is having the capacity of 16-bit. So in order to access the memory, it requires 20-bit address. To convert the 16-bit address in terms of 20-bit address, a physical address calculator block is available, which will automatically convert this 16-bit address in terms of 20-bit address. The physical address calculation will add the particular segment address along with the offset address, which is available on the instruction pointer. The segment address is multiplied with the 10 or a 0 binary. A decimal digit 0 will be added to the least significant byte. So the segment register content will be having 16-bit of data. The instruction pointer register will be holding the value of offset address. The decimal digit 0 added along with this least significant byte of segment register content will convert the 16-bit in terms of 20-bit, as the 0 includes 4 zeros, will add 4 zeros to the lower byte. So the 20-bit converted value will be added with the instruction pointer to access a particular memory location of memory block. The bus interface unit is having an instruction queue, as this 8086 has the capacity of parallel processing. So the instructions will be taken, instruction lines will be taken from the memory and kept ready in the instruction queue. Totally 6 bytes of instruction can be placed in this instruction queue. So whatever instruction lines taken for execution will be placed, 6 bytes of instruction can be folded here. From this instruction queue, the instruction will be taken to the instruction decoder block. So the instruction decoder block will convert the instruction lines in terms of binary bits, machine understandable language, and the instruction decoder will convert the binary instruction in terms of binary bits and provide for the arithmetic logic unit for performing the arithmetic and logical operations. So within this execution unit, it is having a general purpose register block and index registers. So whatever data which is available along with the program lines can be stored in this general purpose registers. So from the registers, an arithmetic logic unit can access the data. So the registers are available in order to speed up the microprocessor operations. Instead of taking the data from memory for each instruction, instead of taking the data from the memory, it will take a lot of time. So the data can be stored in the general purpose registers, and during the execution of instruction in the ALU unit, the data will be taken from this register block, and after completing the execution, the result can also be stored in the registers, and from this general purpose registers, the data can be moved to the memory block. So four general purpose registers: AX register, BX register, CX register, and DX registers. So AX and BX can be used for common for all arithmetic and logical operations. So CX register is commonly used for indicating the count value, or it can be used to indicate the carry. And DX register is used for multiplication and division operation. So other than this four general purpose registers, so four index registers are available. So the index register will hold the offset address. So the stack segment base address is available on stack segment register, and the offset address is holded on stack pointer. Whenever the code segment is accessed, the instruction pointer will be providing the offset address, will be holding the offset address of the next instruction line to be executed. And other than this instruction pointer code segment access, the remaining three segment of the memory, the particular memory location offset address can be stored in this any of these index registers. So base pointer and source index, destination index. Source index and destination is used whenever the string data is accessed. So for string data access, it is possible to move the data from one memory location to another memory location. So whenever you want to access a data between the memory locations, you need 20-bit address. So the particular memory location address, offset address will be stored in the source location address will be stored in source index, and the destination location where the data to be moved, that offset address available on the destination index. So base pointer can be used for data access, the offset address where the data can be stored. So the control system block will generate the control signals required for this entire microprocessor architecture. The control signals such as read signal, write signal in order to take the data or to transfer the data, and the bus signals, so system bus signals, address bus, data bus, and the control bus signal. To access that bus, you need a control signals. So examples as hold signal, hold acknowledgement signal, interrupt signal. So all these control signals will be generated by this control system, and the arithmetic and logical unit will be performing the execution of the instructions. All the functions to be performed in this microprocessor will be done only on the arithmetic and logical unit. A 16-bit flag register is available, which is used to indicate the status of the function to be functions performed. So the example how the physical address is calculated can be shown like this. Consider the code segment addresses 348A, so 4 digits, Each digits can be represented in 8421 codes as 4 binary bits. So 4 digits you can get 16 bits. So for physical address calculation, the segment register content, the lower byte will be added with 0, that is 10 will be multiplied with this, so it will be converted as 5 digits. So 3480A is the value available in code segment register. It is multiplied with 10 and it is converted as 20 bit now, 348A0. So this 20 bit is converted in terms of binary bits, sorry, this 5 digit is converted in terms of binary bits as 20 bits, and it is added with the offset address which is available on the instruction pointer. 4214 is the value available on instruction pointer. Adding these two content, you can get a 5 digit value. So 5 digit it can be converted as 8421 code. Using 8421 code, each digit can be converted as 4 bits. So 5 digit, 5 into 4, we can get a 20 bit address. So that 20 bit address will be pointing a particular memory location of code segment. So about the flag register. So flag register, the capacity of flag register is 16 bit. So among the 16 bit, only 9 bits of flag register content is utilized. So the 9 flag bits, it is divided as two parts, conditional flag and control flag. So from the name you can get the meaning of conditional and control flag. So conditional flag will update the status of the function performed by the microprocessor, and control flag is used to change the execution of the program. So the conditional flag here is carry flag, parity flag, auxiliary carry flag, zero flag, sign flag, and overflow flag. So whenever during the program execution of addition, subtraction, the carry flag will be updated if a carry or a borrow will be obtained, or during the negative number indication or subtraction or addition to indicate the smallest number or largest number. For calculating the smallest number or largest number, the carry flag will be updated. Whenever the carry flag is changed to one condition, the user can identify that a carry is obtained or a borrow is obtained. Parity flag for indicating the even parity. So the result obtained during the execution, if the parity is even, if the value of result is folded with even parity, it will be indicated here as one condition. If it is odd, it will be indicated as 0 here. So auxiliary carry flag is nothing but, so if the carry is generated from the lower nibble, so lower nibble is nothing but, so I am considering an example here. So 0 1 1 0 1 0 0 0, so I am taking an 8-bit value, so another 8 bit of value. I am adding these two values, so 0 plus 0 0, 0 plus 0 0, 0 plus 0 0, 1 plus 1 10. So the sum is 0, carry is 1. So during the lower nibble I am getting a carry, so this carry will be indicated as auxiliary carry here. And for any particular function in the microprocessor during program execution, if the result is 0, the 0 flag will be updated. If the result is a negative number, the sign flag will be updated. And overflow flag is nothing but, so if I am adding two 8-bit numbers, so if the result is a 9th bit, one more bit, so if it is not able to hold within that particular register, so then overflow condition will be indicated. And 3 control flags: trap flag, interrupt flag, and direction flag. So trap flag is nothing but, it is a single step mode operation. For minimum mode operation it can be used. So the microprocessor 8086 can perform under two configurations: minimum mode configuration and maximum mode configuration. Minimum mode configuration, a single microprocessor will do the function with its interface circuit. Maximum mode is it can interface with an additional microprocessor, and it can share the bus architecture with the additional microprocessor and can perform the function. So that is maximum mode. So trap flag is a single step mode. An interrupt flag, whenever an interrupt is occurred, either external interrupt or internal interrupt is occurred, the interrupt flag will be indicated here. So by disabling this interrupt, we can change the non-maskable interrupt to maskable interrupt. Ignore the interrupt. By changing the value here, we can able to ignore the interrupt and continue the program execution. So direction flag is commonly used for string data operation, either to take the data from lower order to higher order address, or to take the data from higher order address to lower order address. So that will be decided by this direction flag. Thank you.